Assalamualaikum warahmatullahi wabarakatuh, and good morning to everybody. Today I'll be chairing the keynote session because the original chairman, Professor Engineer Dr. Abdul Aziz Abdul Raman from MALAYA couldn't make it today. So the organizer have asked me to be the chairman. So today we have three illustrious professors who will be presenting on various topics, from catalysis to the challenge of that chemical engineers will have to face, in light of the implementation plan of the Stockholm Convention on persistent organic pollutants. So we will see from catalysis to pollution, and I think these are quite interesting topics. The first speaker is no other than Professor Piyasan Prasesdam, an expert on catalysis. He is currently the professor in chemical engineering at the Department of Chemical Engineering, Chulalongkorn University, Bangkok, Thailand. And he'll be talking about some phenomena in tungsten trioxide on silica catalyst for the metathesis of 2-butene and ethylene. And so I hope
hello, that's fine. Yeah.
Professor ready. So please welcome Prof. Piyasan.
Okay, thank you. Thank you. First of all, thank you, Mr. Chairman, for my introduction, and good morning, ladies and gentlemen. And also thank you for organizing committee to invite me to give a talk in this seminar. Today, I would like to talk about some phenomena of the tungsten catalyst for metathesis of 2-butene and ethylene. This work also, I work with the company, and now we develop the catalyst, this catalyst, and will be commercialized very soon. Yeah. And I will share you after I finish my talk. You can ask me about the catalyst itself and how to develop the catalyst. Okay, let me start about the propylene. Propylene is very important olefin besides from ethylene, because they can use to produce many kinds of the substance, especially PE, PP, that we use for consumer products. The demand of the product from propylene also increased dramatically or exponentially, as the yesterday talk. And how to get the propylenes? Major share of propylene come from the steam cracker. Okay, and as you know that the price of the ethylene of the cracker or naphtha also increase every year by year. And that's why we should find out some other process that can produce ethylene, propylene. There are also the other process that can produce propylene, we call Acidity process, that can also produce propylene from propane. This process is also very interesting up to now. According to we found about the shale gas has more propane. This process will become more important in the near future. And the other one is catalytic cracking. We also can produce the second part of the propylene come from this process. And the last one is the metathesis. Metathesis is also a very important process, because we can ship the ethylene from one type of molecule of ethylene olefin to the other type of olefin by using this process. The mechanism of this process is very easy. Like we are dancing, yeah, two olefins join together with the bond is in parallel, and then they shift to this side and this side to get a propylene. This is a very simple model. And the mechanism of this reaction is we should make a carbene cation. Ethylene should form carbene cations by assist of the acid side in this catalyst. We need active. This is the active side of the catalyst. But to form the carbene cations to the tungsten, it needs acidity, especially bonded acids, to assist to form this compound. Yeah. That's why acidity also has played an important role also for this reaction. And after this, with the 2-butene also inserts to this and form the complex and then release propylene. And release this complex and ethylene come up and release propylene. This is an ideal reaction because from two olefin to be one olefin only. But the story is not easy. According to the lot of active sites, especially isomerization, oligomerization, and after this it also form hogging. Okay. This also how we develop the catalyst with high activity, high selectivity, less coking. Up to now, in the industrial plant, we must be regenerate the catalyst every month according to the coking. How we overcome this problem? Normally, we use the 3 metals, rhenium, molybdenum, rhenium, and tungsten. Two of them are very active also, can work at the low temperatures, but they are very sensitive to the impurities. And that's why the commercial use tungsten instead, because they are less sensitive than impurity. We can operate for a longer time. We believe that the active center of this catalyst is the tetrahedral form of the tungsten. Yeah. But isomerization also can conform this form. The isomerization is a side reaction that we should be avoid. Preparation of the catalyst, it's very simple to prepare this catalyst. We use a tungsten precursor and spin wetness on the silica gels, and then calcite, we receive the catalyst. It's very simple. In general, we cannot separate from tan to butene and cis to butene. They come together. If you separate it, you need the distillation column. It means that you increase your operating cost. Why we can use 2 types of the butene without separations? We prepared 4 kinds of catalysts: 5% tungsten, 7%, 9%, and 11% of tungsten. You can see that when you increase the tungsten loading, the acidity of the catalyst also decreases by measuring by ammonia activity. And in contrast, these peaks show the crystallinity of the tungsten. When you increase the tungsten loading, the crystallinity of the catalyst of the tungsten also increased. This is also not active center. We can measure the active center of the catalyst by measure with the Raman. This area is a peak for tetrahedral, and this area is the crystal that shown by X-ray. We define the ratio of the tetrahedral tungsten and crystal tungsten. If the ratio is high, it means that active sites are high. You can see that in both, anyhow, we have very loading of the tungsten. The ratio of the tetrahedral and crystal are not change much. Yeah. But the amount of tungsten on the surface of catalyst that measured by EDX will be changed. It means that the tungsten, when you higher loading, they are accumulated to be on the surface. This is a TEM image to show the particle size of the tungsten on the cilia. It's formed orthorhombic form of tungsten oxide. This curve shows that when we absorb the mix of butene, tan-to-butene, and cis-to-butene, you can see that when we vary loading of the tungsten, the absorption of the butene are not increased. When compared with the pure butene, the absorption also vary with the amount of the tungsten loading. That is why we can find that at higher loading, the conversion of the mixed butene are not the same, less than pure butene. This phenomena also, we also observe this phenomena, and we can summarize that if the tungsten dispersion are very low, we will have some problem about the absorption of the cis and tan-to-butene. We can draw a cartoon like this. This is the propylene. At the low loading of tungsten, the active center are separate, and then we get four, okay, for propylene. But when we use the high loading of tungsten and mix tan-to-butene and cis-to-butene, we get less product than we expected. We can get less. When we use tan-to-butene only, we get higher product. And when we use mixed tan-to-butene and cis-to-butene, we get less propylene. According to the both are absorbed on the surface of catalyst, less absorption. For the cork formation, we can see that low loading has low corking, according to the low conversion. But if you put between corking divided by conversion, you can see that at low loading has highest cork formation. In summary, we realize that if our catalysts are high dispersion, we can suppress about the effect of mixed two butenes. And our selectivity also increase. But the acidity of the catalyst also increase. That's induced to the cork formation also high. This is in general of this catalyst. How we develop the catalyst? We want them to be higher dispersion, and we want them to low corking. The first step, we want to make the catalyst has high dispersion. We put the extra support. We put the extra support such as silica nanoparticle and also titanium nanoparticle. We want to separate, disperse it to be a planar or monolayer on the catalyst. Yeah. We do like this. After we get the catalyst, we put extra support together and then calcite it, and then we get the catalyst. Very simple. You can see that it doesn't depend on the amount of the extra nano support that we put until 15% weight. Yeah, the conversion and the yield also almost the same. Yeah, and BT also not change much. This slide shows you that, especially at the low loading, for example, 5% of tungsten, if you put 10% of the nano silica, you can push your activity to here, a large gap. It means that you use at the same level as the higher loading. It is about 11% of the tungsten. You see, the activity also the same. 5% and 11%, you can increase, you reduce the cost of the tungsten that you will put on the catalyst. By put only 10% of the nanocrystal, nanosilica, they increase a lot, okay? And at the same time, they also increase the yield of the catalyst. The surface area also not change much. And the crystallinity also not change much. But the Raman, the ratio of the tetrahedral also increased a lot, especially in the low loading of the tungsten. You see? But at the low loading, this is the ammonia TPD. At the low loading, the acidity also increased. It means that coking also increased at this point. Product yield also increased. You can see, especially at the low loading. At the high loading, not change much. The other extra support, we use nano titanium, the same result as the silica. We can see that at low loading of tungsten, 5%, we put 10% of the nano titanium. We increase a lot of conversion and also yield of the catalyst, this yield. By putting only 10% of the nano titanium, the result also the same as the silica. Okay, you also can see that the ratio of active center also increased a lot from the, especially from the low loading of the tungsten. We found that there are some movement of tungsten to the extra support when we separate it and we digest the extra support and measure by ICP. This amount of tungsten occur on the titanium extra support. It means that they move from catalyst to support. We believe that they have some thermal spreading phenomena. They believe, but I don't believe. But if I don't believe, I cannot publish. I should believe, follow the literature. But I don't believe. I believe there are sublimation. Okay. But as you see, they increase the acidity also. When you put the extra support, nano extra support, and acidity increase, cooking also increase. We can summarize that. For this technique, extra nano support, at low loading, the activity are increased a lot, and selectivity also reduced a little bit, but the acidity also high, and coking also high. How we suppress the coke for catalyst stability? We use the other technique. We put sodium hydroxide ionic chain on the catalyst, like this, and calcite. Because you can see that the surface area are not changed much when you put the sodium hydroxide inside. It means that the structure of the catalyst are not changed. But you can see that the amount of tungsten in the catalyst are changed, especially at low loading. We lost a lot of tungsten by leaching with sodium hydroxide. But in the high loading, there is very few loss of the tungsten. Yeah. And for the acidity also, we are sure that the acidity also decrease. In this slide, you can see that at low loading, the acidity also decrease. The conversion, I think this side, the conversion also decrease. But at the higher loading, 7%, 9%, and 11%, even though the acidity also decrease according to sodium hydroxide, but the acidity, the conversion also not change. The conversion also not change anymore. Okay? It has some effect only low loading. And the propylene conversion also, it doesn't, for high loading, it doesn't change much for propylene yield. Or we get a little bit yield. It means that sodium hydroxide ionization is a good way to increase the propylene yields a little bit. But for the coking, when you ionization with the sodium hydroxide, coke is decreased a lot. You can see coke is decreased a lot. It means that we are success to reduce the coke and reduce acidity of the catalyst. In summarize, for ionization of sodium hydroxide, at the low loading, we are not successful because we lost of conversions. For high loading, it's okay. The conversion is okay. Selectivity increase a little bit, but we suppress coke. In overall picture that we develop this catalyst, we say that this catalyst should be high dispersion. How to make it high dispersion? We will put the extra support. Extra support can increase dispersion, but we cannot reduce the coke. But if you put the sodium hydroxide ionic chains, you will suppress coke, especially for high loading of the tungsten. Okay, thank you for your attention.
Thank you, Prof. Yasan. we will reserve the question time after all three presenters have presented theirs. So Professor can sit for a while, and then later they will ask questions. So please note whatever you want to ask Professor, and then ask it at the end of the session. The next speaker is Professor Dr. Muhammad Ali Hashim. He is a professor of chemical engineering at the Department of Chemical Engineering, University of Malaya, the oldest university in Malaysia. His main work is in liquid ionic, but today he's not going to speak on liquid ionic, but on catalysis, a new type of catalysis for biodiesel production, which is an organic acid to replace the currently used mineral acid. So he will be talking about novel organic catalysts for the processing of low-grade palm oil into biodiesel. Just for your information, Professor Muhammad Ali Hashim was director of the science division at the Ministry of Science for some time ago. And he's a very well-known professor in chemical engineering in Malaysia. So please welcome Professor Muhammad Ali Hashim.
This one is the sky. Okay, thank you very much to Professor Dr. Ramli for the introduction. I'll use this. Assalamualaikum and selamat pagi to everyone. Firstly, I would very much like to thank the organizing committee for this invitation. So the title of the presentation is, as you can see on the board, Novel Organic Catalyst for the Processing of Low-Grade Palm Oil Diesel. Now, the main points or the main contribution in this work, there are two. One is the use of, we are able to prove, this is a work which has been completed by, part of a PhD work completed by a student I supervise. There are two things here that he has done in this particular work. That is to introduce a new industrial crude palm oil, which is a mixture of acidic palm oil, which I will explain much more later, and a slush palm oil. It's a mixture that is used at a fixed speed for the production of biodiesel. And the other major contribution here is the introduction of camphor sulfuric acid, which is an organic acid in esterification process in the production of the biodiesel. So these are the two main points that I would like to highlight in this presentation this morning. So this is the person who did the work, and I would also like, his name is Adib, Mr. Adib Hayang, and the other one is his brother who also completed his PhD with me about 2 years ago. And the other point that I want to make here is to acknowledge funding from the government. Now, I have a number of slides that I believe will give a good introduction to this topic, especially to people who are not from Malaysia. You may not be very familiar with the palm oil industry, and some of you are probably not so familiar with biodiesel as well. So the first few slides may help. Now, this first slide is simply to tell you that what biodiesel is. It is actually methyl No, actually it is alkali ester. This could be ethyl or methyl, but in most cases we have been working on, it is the methyl ester, sometimes abbreviated as FAME, FAME, fatty acid methyl ester. That is biodiesel, the chemical name. And FAME is just abbreviation that most people use in the people who work in biodiesel. So biodiesel, as you can see from this slide, the feedstock can be vegetable oil or animal fats. So what are the benefits of biodiesel? Again, this because I noticed there are quite a number of students in this audience, so I thought that maybe a little bit of background will help to show you the importance of biodiesel. Here are the importance. Emission is low when you burn them, so you have very little problem with air pollution. And the other point I mentioned in this slide is that biodiesel, as it is now, is mostly used blended with the conventional diesel. And the percentage varies according to the regulations in different countries. In Malaysia, it is 5%, but it's going to be 7% very soon. In countries like US, it is about 10%. There are some other European countries that use a higher percentage. And you don't have to do anything to the engine. This is as long as you keep to the percentage that is already regulated. Yes. And the other thing about biodiesel is that it is non-toxic, renewable, therefore sustainable. So sometimes it is called a green fuel. Now, what are the challenges in biodiesel industry? There are two major ones from what I can summarize. One is the raw material, and the other one is the production cost. Now, there is a controversy in the use of something which can be used as food to be used and turn it into a fuel. The cost of raw materials account for 60 to 70% of the total cost. In Malaysia, there has been an increase and interest in the utilization of the palm oil as a raw material for biodiesel production. But this interest is not from the crude palm oil, obviously, because crude palm oil can be turned into many different types of foodstuffs and also for other purposes, which I will mention again later. But what we are dealing with are things that otherwise will go as waste. So this is the main thing. And the other point of the use of raw material is that the raw material from other feedstock may not be much in abundance. For instance, you can use crops like jatropha, you can use rubber seeds, you can use tobacco seeds, but these are of very limited availability. And therefore, this is where the palm oil industry can help. So that is the raw material part. The other part here is the production cost. When we talk about production cost, this involves the chemical use, the catalyst use, the reactors, and the technology that is applied. There are a number of technologies for the production of biodiesel. And two of them I can cite is supercritical extraction, and the other one is enzymatic reaction, but these are very expensive. So the popular one is chemical reaction, but even in chemical reaction there are also issues or problems. For instance, what type of reactor do you want to use? What type of catalyst? These are the questions that you will ask. So, as I mentioned earlier, as far as raw material is concerned, we have plenty and in abundance. So just look at the palm oil industry in countries that are growing palm oil. Malaysia is said to be the second largest producer of palm oil. And we are producing close to 20 million tons on approximately about 5 million hectares of land. So a lot of our land, agricultural land, is used for this. Now, as the palm fruit matures, it can produce 30% of the mesocarp weight of palm oil. Sometimes it can even go, depending on the species used, can even go to 50% of the mesocarp weight. So there's a lot of palm oil. And the next slide also should tell you. Now these slides give you the prices. It's a bit outdated, but it gives you some indication. So, but as I mentioned earlier, it has a very high commercial value, palm oil. And we need to identify the low-grade, non-edible portion that we can use as raw material for biodiesel. That is not competing with the one that you use for foodstuff. Now, which portion? Now, to answer that question, again, some basic thing about palm oil industry. There are two major steps in the processing of palm oil. One is the milling process, and one is the refining process. What is shown here is the milling process. The milling is to extract the crude palm oil, as you can see from this diagram. There are a number of stages. Now, this number of stages yielded two major byproducts. One is the empty fruit bunches, and the other one is this one, the acidic oil. The LG here means low-grade fruit palm oil. SPO here means slash palm oil. Now, a main point to be registered is that refinery, that means after the crude palm oil has been milled, you would want to have to go to the refinery for refining. But refineries will not accept anything greater than 5% of, if it contains 5% of FFA, free fatty acid, refinery will not accept. Because it will not be considered as food grade material for further processing. Now, before we go further, what do I mean by FFA? For people who are not very familiar. Now, FFA are I'll come to FFA later. I think I have to try. I'm trying to follow in a very logical way. Okay. Now, FFA, free fatty acid, is obviously there are the good portions and there are also the non-good portions. The good, what I mean by good portion are those that can be used as food, as a feedstock for food materials. The other one, which is the saturated one, will be used for other purposes like for cosmetics, etc., etc. Now, how does the FFA build up in the fruit? For a number of reasons. Some of you who have not been to palm oil plantation will not know this. This is due to the enzymatic attack. The enzyme is called lipolytic enzyme in the ripe fruit. Lipolytic, and the increase of FFA is due to a number of reasons. One is bruising of the fruits during harvesting. If you don't harvest, if you are not careful during harvesting, the FFA will build up in the fruits. Storage can also cause a build-up of FFA, and also things like change in weather condition can also give problems to the build-up of FFA. And even, of course, in the milling process, technical problems in the milling process can also cause this build-up. Now, okay, the byproducts of the milling process, I have already mentioned. Okay. Characteristics of MIPO. This MIPO is referring to a mixture of the slush and acid crude palm oil. In the work that we did, we add about 8 to 10% of the slush into the acidic crude palm oil. And from our test, it doesn't change the characteristics so much. But here are the characteristics to compare between the crude palm oil, the one that will go for refining, and the waste, the mix, which I mentioned just now, mixture of the acidic palm oil and the sludge palm oil. So you can see that I will concentrate on these three parameters. This will tell us that whether the oil is edible or non-edible. As you can see from the comparison, you take, for instance, the peroxide value. Sorry, the peroxide value. The peroxide value here is 6.37. This is extremely high. Now, peroxide value tells us the potential for oxidation. It tells us the potential for oxidation, and there are many byproducts of this oxidation. Some of the product can even be carcinogenic, but then if we are using this for fuel, then it doesn't matter very much. The other thing that I should mention here is that the high moisture content. The high moisture content can also cause problems can cause other problems. There are many problems that moisture can cause. So as I said earlier, the blending of the sludge palm oil with the acidic palm oil doesn't change, will not affect esterification. Esterification is the other step which I will mention afterward. So the contribution here, as I indicated earlier, is that we are able to show that the sludge palm oil can be mixed with the acidic palm oil as a feedstock for biodiesel production. And as far as we know, this has not been done before anywhere else. Now, just now I mentioned about the various fatty acids. So these are the fatty acids. So here are the saturated ones that cannot be used. And these are the unsaturated ones. So this is the one that can be used as food, and this is the one that are not suitable as food. There are two major steps in biodiesel production. I have mentioned earlier esterification. The other one is trans-esterification. Now, conventionally, if you look at the process, now this is esterification is simply the reaction between the FFA, and methanol in the presence of acid catalyst. A normal catalyst is H2SO4, and this is the biodiesel I mentioned, and the other byproduct is water. Okay, so now sulfuric acid, as you know, is corrosive. It is also obviously hazardous. Difficult to store, difficult to transport, and as far as we know, and we have tested, it's not recyclable in this kind of process. So what do we do? What we have done is we have introduced a new catalyst for this process. We have tried many different catalysts, and this is one of them. That is what I mentioned earlier, the novel organic catalyst, camphor sulfuric acid. Now it is in powder form, therefore it is easy to store, it is easy to handle compared to sulfuric acid. And this particular diagram just simply tells you that after we have done esterification and we reduce the FFA to 2% or less, then only we can have alkaline catalyst for the trans-esterification process. If you don't do this, you'll be wasting your oil because you're just making soap. That means if you don't reduce your FFA. So the treated oil, as I said, will undergo trans-esterification to produce our product, the biodiesel. Now, I have also mentioned just now the advantages of this type of catalyst in comparison to H2SO4. Now, we investigate a number of parameters, but this morning I am just going to concentrate on four important parameters that will tell you how efficient this new catalyst is. One of them, the first one, is the effect on catalyst dosage. So here there are a number of lines, two important lines. This line is telling you the drop of the free fatty acid to 1% FFA, which is now ready for trans-esterification. This is the esterification process. Once you reach 1 or less than 1, our optimum is 1, so you don't have to use so much. This is the dosage of the catalyst. So we are talking about a dosage of about 1 here, but in our experiment we use just slightly more than that, for 1.5%. This is comparable to the amount that is used when the reaction use H2SO4. So, but we have very good conversion, as you can see here, close to 95%. This is the conversion axis. But the most important thing is this limit, the dotted line, which you'll see again in the next slide. So again, they're showing you the dotted line. You have to reach this level. This is for the molar ratio of methanol to the catalyst. And in this case, the optimum ratio we think is just about 10 or slightly more than 10 for us to be able to carry on the process without much problem and getting to again a very high conversion percentage. So this is the other important parameter. The other important parameter that we deal with, or I want to show here, is temperature. And temperature, the type of temperature. Now, the reaction temperature that was optimized is in the range of 40 to 80 degrees centigrade. The lowest temperature, as you can see, is about 40 degrees centigrade here. Temperature is important to make sure that we don't reach the boiling point of methanol, which is 64%, and therefore we keep that at about 60 degrees. Methanol boil at about 64 degrees centigrade, so we are keeping that at 60 to get the optimum. So this is temperature. The other parameter that is reaction time. Now, reaction time, just for comparison. Here you can see very clearly, if you have been following what I said. That is the 1%. So after 30 minutes, we are able to progress with the conversion up to almost 95% conversion, or close to 90% conversion. And if you compare with H2SO4, you will require a temperature of, you require a reaction time of 60 minutes. So this shows the efficiency of this catalyst in comparison to the conventional H2SO4. Now, the other important aspect about this catalyst is that in this case we are showing that when we can recycle for 6 times and we still have good conversion, which you cannot do with H2SO4. If we use about, in the experiments that we have undertaken, if you use about 1.5% weight catalyst, just to give you some idea, we are able to produce about 200 grams of, we can produce the biodiesel, but with 1.5% weight catalyst using 200 grams of the feedstock. That is the mixed acidic crude palm oil and the slush oil. So how does it compare to the standards? Okay, there are two standards. This is one of them is the European one, the other one is American. You can see the American volume was the first four. The point that I want to make also here is that most important point is that we are able to reach the standards that is required internationally. So the biodiesel is as good as any other biodiesel. And other thing is the CPN number. We have very high CPN number. We may lose a little bit in terms of viscosity, but work is being done more on the viscosity side. This work has been written up and in chemical engineering science, so you can get more details on this work that I've just presented in chemical engineering science. We have done, as I mentioned earlier, other acids as well. So this is part of the PhD work. These are the other acids that have been tested. And they are all written up, and you can get the details in all this journals. So this is something which my student wanted me to show. What I've said just now, from the he starch kit, goes to biodiesel, use the catalyst, go to the engine, and get this bus running. Thank you very much.
Thank you very much, Prof. Muhammad Ali Hashim, for telling us about a new type of catalyst, acidic catalyst for biodiesel production. And as he has mentioned earlier, that Malaysia is now introducing biodiesel 7% of biodiesel is being put in the B7. So from 5%. So very soon we'll have the B7. The next speaker is Professor Dr. Susan Gallardo, who is presently a Professor of Chemical Engineering at the De La Salle University, the Philippines. She's very active in the area of persistent organic pollutants, and she'll be talking about how chemical engineers can participate in reducing or converting POPs to something that can easily be degraded in the environment. So I would like to welcome from Susan Gallardo.
Good morning to everyone. It is my pleasure to give a lecture related to something that we just completed in the Philippines, and that is the drafting of our updated National Implementation Plan on the Stockholm Convention for Persistent Organic Pollutants, or we call that as POPs. I would like to thank first of all, De La Salle University, our department, for recommending me to present something on environmental engineering, and for the invitation given by the organizers of RSE 2014 this morning or today. Okay, so why did I choose this topic? It's precisely because I wanted to share with you the process by which we were able to draft or formulate the National Implementation Plan for the Philippine government. I come from the academe. I work as the director of the Asian Regional Research Program on Environmental Technology, which is actually the National Research Institute for Industrial and Hazardous Waste. But this national implementation plan is supposed to be a work of the Philippine government. But because of the lack of expertise of the Environmental Management Bureau of the Department of Environment and Natural Resources, this project, which is actually funded by the Global Environment Facility and implemented by UNIDO, all the logos are there, actually was endorsed to RPET, the LSU. Okay. So today I'd like to share with you the process and also to fit the theme of this regional symposium, I would like to mention some of the challenges that the chemical engineers can face in regards to implementing this NIP in the future. And of course, these challenges open doors to what we call opportunities for projects that can be done by various sectors of the countries, be it the industry, the academe, and other research institutions, and even the Philippine government. So I will talk about, first, something on POPs, persistent organic pollutants. Are you all aware of these POPs? May I see hands of those who are already familiar with POPs? Okay, so I'll talk a little bit about that. Are you aware of the Stockholm Convention? Please raise your hand if you're familiar with the Stockholm Convention. Yeah, of course you are our consultant, Dr. Arcena. You should be aware of it. And then how about, I'll talk a little bit about the Stockholm Convention. And of course, I will present to you later on the NIP of the Philippine government. So what are POPs? So actually POPs are actually toxic substances that have harmful effect on our health as well as the environment. Most of these chemicals are chlorinated compounds or brominated compounds that persist in the environment for a long period of time. And these POPs are mostly consist of pesticides, okay, industrial chemicals that we use or may be incorporated in the final product that is for final consumption, or it can be just a byproduct of some industrial activities and even burning of waste. So what are the general properties of POPs? Aside from being toxic, it is actually persistent. It actually resists many forms of degradation, be it biological degradation or chemical degradation. Another property of the POPs is its bioaccumulative property. It means that it can be passed on from lower form of life to higher form of life. Most of these POPs are fat-loving. So they are sometimes not soluble in water or maybe slightly soluble in water, but it binds tightly into fats. So you will see them actually in the fatty tissues of fishes and other animals. And when you say bioaccumulative, it means that it can be, when you eat the fish or you eat the fatty tissue of the beef or the animal, it can be passed on to you. And it can be passed on to the fetus of the pregnant women. And not only that, it is not only bioaccumulative, but it is actually biomagnifying. So the concentration of this in fishes is lower, but if you look at the concentration of this in the breast milk of lactating mothers, you will see the concentration is 1,000 times. These are studies that have already been verified. And it is capable of long-range transport. It can be transported through air movement, through advection and condensation. In fact, when they tried to analyze animals or mammals in the Arctic region, they found in the fatty tissues actually traces of pesticides, and they are not used there. And it can be transported also through migratory birds. So the birds eat this contaminated sediments, and this actually is transported in another region through the migration of this animal. It has various adverse health effects, and one of them, of course, is can cause cancer and tumors. It is actually an endocrine disrupting substance. It has also effect on our temperament because it has can have neurobehavioral impairment. And it can also have what we call immune system disorders. One of the things that we always highlight in our presentation is actually its effect on reproductive deficits and sex-linked disorders. So I always show this picture whenever we go around the country to make them aware of the effect of the POPs. And I always ask whether this is a woman or a man, and nobody can tell. Because POPs actually can cause feminization of males and can also cause masculinization of female. And so there. I actually added this picture. This is the picture of Raquel Carson. Raquel Carson wrote a book. Have you read this book? Silent Spring? Anybody? Actually, yes, of course you are. Okay, you are also part of ARPED. Silent Spring is actually the first documentary that actually shows the effect of DDT, which is a pesticide, on the bird's eggs. Usually during spring, the birds appear, and so you can hear them chirping. But suddenly, there was a time that there was no more chirping. So it was a silent spring. So when they investigated, they found out that the birds are contaminated with DDT, and it can cause the thinning of the bird's eggs, shell, and it is never hatched. So that is the reason why it was entitled the Silent Spring. And this was the first documentation, and after this, there are already several investigations done and studies on the effect of the POPs. So what is the Stockholm Convention? Because of the effect of this on health and the environment, countries from different parts of the world gathered together in Stockholm, Sweden, and adopted what we call the Stockholm Convention on POPs. And the purpose of this convention is really to restrict and finally prohibit the production, use, release, import, and export of the POPs. The treaty actually agrees on year 2027, POPs will be eliminated from our environment. So, here is a timeline showing what are these chemicals that are listed in the Stockholm Convention. It was in 2001 where these countries actually signed the treaty, and of course the Philippines is one of the signatory countries and adopted actually the listing of 12 POPs, and these are called collectively as the 30,000. Now, the POPs Review Committee every 2 years submits to the Stockholm Convention Secretariat what we call candidate POPs. And so added POPs are reviewed by UNEP, and the risk assessment are done. And it was in 2009, during the Conference of Parties, Fourth Conference of Parties, where this convention was amended to include, again, 9 new chemicals, and they are called the nasty nines. And in 2011, another review was made by the PAC-RC and again amended this convention to include N-busulfan, another type of pesticide. And more lately, in 2013, last year, about December last year, they amended again to include HBCD. So here are the list of the dirty dozen. The first 8 are pesticides. We have industrial chemicals like hexachlorobenzene and polychlorinated biphenyls or PCBs. And dioxin furans and HCB are also considered unintentional byproducts of industrial processing, and dioxin and furans are actually byproducts of what we call burning activities. All of these are pesticides. They can be termiticides or fungicides. Here are the listing of the new PACs. These are the nasty nines. Those with 1 asterisk, such as chlordicon, alpha HCB, and beta HCB. These are what we call the new PACs pesticides. And the rest are what we call industrial chemicals. 1 PECB is actually an unintentional byproduct. The convention actually has 3 listings in 3 annexes, Annex A, B, and C. When the chemical is listed under Annex A, it means it is for elimination. So parties to this convention must take measures to eliminate the production and use of the chemicals, while those that are listed under B are restricted. Okay, they can be used for certain acceptable use. So parties to this must make measure to restrict the production and use of the chemicals. And lastly, Annex C. Annex C is where you list all those unintentional byproducts of activities, but parties must take measure to reduce the releases of these unintentional byproducts, so that at the end, it can ultimately be eliminated or minimized. Here are the listings of this now total of 22 PACs, no, in the Stockholm Convention. So listed under Annex A are all the pesticides in the dirty dozen except DDT. DDT is restricted because it is still used for malaria control. And another listing in the Annex A is endosulfan, which was added in 2011. Annex A also lists all the other industrial chemicals found in the nasty nines. And Annex B also lists PFOS, which is actually another industrial chemical listed in the nasty nines. Dioxin and furans is under the dirty dozen. It is listed under Annex C, and PECB also is listed under Annex C. So what is the National Implementation Plan? It's actually a what we call a framework, a legislative and institutional framework that lists down action and strategy plans on how these chemicals can be phased out or eliminated from the environment. The Philippines actually is a party to the Stockholm Convention, and Article 7 of the Stockholm Convention says that all parties to the convention must make effort to comply with the Stockholm Convention. So a NIP is required. The Philippine government, being one of the signatory countries, came up with the first NIP. This is the first NIP for the dirty dozen in 2006. And because of the additional listing of PACs chemicals, the nasty nine and endosulfan, the Philippines is one of the countries now assisted by UNIDO to review and update our National Implementation Plan. So in 2012, UNIDO PAPS Management Officer, Dr. Centeno, actually presented some of the countries who are being assisted by UNIDO in terms of updating and reviewing their PAPS at their need. And the Philippines is one of them, under Asia and the Pacific, Indonesia, and Mongolia. This is not yet updated, that was 2012, but in 2013, Vietnam, okay, and Thailand are added as two countries that are assisted by UNIDO. So Philippines was one of the first countries that received this grant under the GEF funding through the UNIDO. And this actually grant is supposed to be given to EMB, which is the focal point for PAPS management in the country, but it was endorsed to De La Salle University, to our research center. The process of reviewing the need consists of what we call 5 phases or 5 stages. And in the process, we followed what we call a guideline that was provided to us by the Stockholm Convention Secretariat. These 5 phases includes the establishment of a coordination mechanism and organizational process. Actually, it was not difficult for us to establish this because the PAPS Management Office already established when we had our first meet the coordination mechanism. We call it the National Steering Committee for PAPS Management. So it was just re-established and reactivated in the updating of the NIP, but more members of the steering committee were added, and this includes more of the representatives from industries. And the second step is the establishment of PAPS inventories and assessment of our national infrastructure and capacity. So this is one of the difficult tasks that we face because we have to deal not only with the government, but we have to deal with other stakeholders such as industries and of course the farmers. Okay? And then we have the priority assessment and the objective setting after the second phase. We have the fourth phase, which is actually the formulation of the need, and finally the endorsement and submission of the need. That particular grant was performed by 4 components, 3 coming from De La Salle University. Component 1, it performed the first phase, which is actually the coordination mechanism and organizational process together with the EMB. Component 2 was actually performed the second phase on inventory and assessment. Component 3 actually performed the third and the formulation of the need, and the last, which was performed by the government, is actually the endorsement and the submission of the need. Up to this point, the submission to the Stockholm Convention is not yet accomplished by the Philippine government. How did we approach the need? How did we prepare for the need updating? Of course, we have the different enabling activities which I mentioned, but we make use of the guidelines, or what we call guidance document of the Stockholm Convention, and we base also these from experiences that other countries have. But it was very difficult because actually we are the first country in Asia that is able to update our need. So we had a workshop in Vienna where Macedonia who also shared their experiences with us. So we were able to share experiences. And of course, we have the many involvement of the stakeholders through what we call interviews and survey forms and workshops that we did. So here are the output of the different components. The first is the reception workshop, which actually gave awareness of what are the PAPS issues, including the new PAPS, the Stockholm Convention, and the development of the updated need. And of course, we secured the participation or commitment of the different stakeholders, and the political commitment was also made to successfully develop and formulate the updated NIP. The second was accomplished in 2013, July, and this is through the inventory validation workshop. So here, the output is actually the assessment of the national infrastructure and capacity of the country, as well as the inventory of the new pumps and the review of the old pumps. And next is the next accomplishment was in October 2013, component 3, through what we call, it was presented through the priority setting and reformulation workshop. This actually component did what we call a situational and gap analysis with the help of component 2, and then they developed criteria for priority setting, and finally the strategies and action plans were formulated. So this was the last accomplishment this year, just lately, August 20, very timely for the invitation given by the organizing committee for me to give a keynote lecture. So it was just in August 20 when De La Salle University endorsed it to the Environmental Management Bureau. So what are the challenges of the chemical engineers, and what are these needs? The need consists of 30 pages. I just will highlight a few of these need and some of the challenges, and I'm given only 2 more minutes to wrap up. So let me just give you some of the highlights. Chemical engineers are challenged to work together with environmental engineers, as well as what we call the government agency like the Fertilizers and Pesticides Authority in the monitoring and as well as the detection of these pumps. So I think this is where we are challenged to come up with projects with the government so that we will be able to have an accurate inventory and assessment of the problem on pumps, pesticides, especially the new pumps, which is actually lindane in the country. And you can see that one of the strategies is to ensure environmentally sound treatment infrastructure for storage and disposal. Again, chemical engineers are challenged to come up with alternative storage. You can see the storage are all corroded. So there is a need to come up with material so that while waiting for a good destruction facility for these pumps, they are stored soundly. So this is another challenge for chemical engineers in coming up with alternatives to these pumps pesticides and also pumps chemicals, and come up with best agricultural practices. And of course, as chemical engineers, we can do what we call cost-benefit analysis. And for PFOS is a chemical that is used in open application and closed application. So sometimes you will find it incorporated in your final product. So if you're familiar with Teflon before make use of PFOS, no? As one of the chemical. And so here we are challenged again to come up with alternatives to PFOS. PFOS is listed under Annex B, so it is restricted. So there is a need to come up with alternatives so it can be finally eliminated. This is a challenge again because what the group did was an initial inventory. So we only did inventory tier 2. So we are challenged to come up with a more comprehensive what we call inventory, and that is the tier 3, where you have to do actual sampling and analysis of the products. Actually, in the country, this is actually a result of the inventory using what we call importation data and using what we call emission factors formulated by what we call by the Stockholm Convention. So you see, 84% of the total industry that contributes to PFOS use is the metal plating industry. And this is followed by the pulp and paper industry. And we have also firefighting substrate, printing ink, semiconductors, electronics, and also it is used in packaging substances. So there are many other PBDE. There are also challenges because PBDE is under Annex A. It was banned to be produced in 2004. It is mainly used in electronics as well as in plastics as a flame retardant. But the problem is second-hand. The Philippines is a problem on second-hand, what we call use of PBs and the EEEs coming from Japan. So even if it is already banned in 2004, because we are receiving these articles, we have a lot of PBDE. And what we are doing what we call a lot of recycling activities. So these are challenges to chemical engineers to come up with isolating or screening or separating the hazardous component that consists of PBD and being able to recover those that can be recycled. We have also additional, because before we have the need for PCBs, we have additional challenges for PCBs. We already have our destruction plan, but there is a need to come up with technologies for not only destruction of stockpiles, but also destruction of PCBs in soils and in water. We took up the challenge, RPET, actually in 2001. And then, of course, the UPAPs, the continuous updating of the emission factor, okay, that is actually done by UNEP before. This is also where chemical engineers can work with, no? And that is developing technologies to decontaminate the contaminated sites. We have also what we call IEC action plans, and this is where the people from the academy can work together with the government in awareness and education of our of the different stakeholders. So let me introduce at the end the members of the project coordination unit. Most of them are chemical engineers, and I think some of you know them. They are here. We have Engineer Dario, who will be presenting this afternoon. We have Dr. Abelia, Dr. Borja, Dr. Estrella, Dr. Mike Comentilla, Engineer Denver, Dr. Arisena, and our students. All of them are chemical engineers. And we are all responsible to come up with the national implementation plan for the Stockholm Convention for the country. So thank you very much and have a good day.
Thank you, Professor Dr. Susan Gallardo. I'm told we have 10 minutes of Q&A. So I would like a question for each of the presenters this morning. Can anyone start the ball rolling? Yes?
Yes. So, my name is Nadia. I'm a student of degree in chemical engineering. So, to the second presenter, there are many kinds of fatty acids present in palm oil. And then, how do you separate these acids? First, fatty acids, and then which standards are more reliable? And how do you compare together with European and American standards, especially in biodiesel?
Thank you. the separation is done through chromatography technique. The one that I showed on the slide, the different 6 fatty acids, I think, is through GCMS. Okay? GCMS analysis, the one that you saw on the slide, one of the slide. The other question is about standards.
Yes, standards compared between liquid and American standards, and which one is more viable?
I think we tend to use, if I'm not mistaken, we tend to use more of the American one. Yeah. STM. Sorry? They have more parameters in them. Yeah. I think you can see that I also pointed out when I showed the slide that I think at least 4 or 5 of the parameters are not mentioned at all in the American standard. Because it doesn't make sense also, you know. So I say that because of a number of reasons which I don't want to elaborate. Yeah.
Thank you, Prof. Next question to the other two presenters this morning. What? Everything crystal clear? Yes? Anyone? Maybe I should ask Prof. Biasan, if you don't mind. The main problem with metathesis is, of course, the selectivity for industrial use, apart from the revoking and so on. What is the level of selectivity that the industry would want to make this commercial, this catalyst?
Yeah. In general, I understand some of you are not work in catalysts. That was why I am very happy, because there is no competition for me. If all of you work on catalysts, it's more competition for me. Yeah? In general, we need 100% conversion and 100% of selectivity. In nature, the selectivity is 100%, but conversion is less. In chemical industry, the selectivity, the conversion are very high, but selectivity are low. Selectivity means loss of feedstock, right? That was why that in your question, we also try to reduce the loss of the feed, right? Okay, by improve the selectivity. It means that selectivity are very important. The selectivity and conversion, if we multiply together, we will get yield, okay? Normally, industry prefer the yield about more than 40% of yield, yeah. And we try to reduce the loss of the feedstock. It means that try to increase the selectivity as possible.
Okay, thank you, Prof. Okay, the third question to the third presenter. Anyone? It's not K-pop. Okay. it's just pop, no K. Anyone? Maybe the awareness of POPs in Malaysia and other ASEAN countries might not be so well disseminated. So that's why most people are not familiar with POPs. They are familiar with K-POPs, but not POP. So anyway, if there is none, then I would like to hand over. Yes. Oh, my comment. Okay, right. So, all right, please. Can you give the mic to
To respond to that comment, that's the usual comment we also get when we went around, when we did our IEC for the new POPs. So very few of the different stakeholders actually know that PPOS and PBDE are already banned and under the Stockholm Convention. And if you tell them whether they know, whether they are pollution control officers, most of them are chemical engineers, they even do not know that their product already contain those chemicals. So I am not really surprised for that comment. And this is the reason why I wish to share with you this presentation or this lecture. So I'm happy that at least now you know what are POPs and the effects. And maybe in the future or in the near future, somebody could take up the challenge of seeing whether your environment is free from POPs. Okay, because by 2027, we would like to accomplish a POPs-free environment globally.
Thank you very much for the clarification. So I would like to pass the baton back to the MC for announcement or the next.
We're just going to take this little bit of time to give opportunity to the next host of SOMJ and RCHE to just give a bit of insight on what's going to happen next year, so for 2015. So what I'll do first is invite the host for the RCHE 2015, which is Dr. Anjilamon Matanko. Sorry to say it. So you have the slide.
That's the next one.
That's right. How can I move this one? This one, huh? Next for the move the slide.
Next.
Forward, backward, forward.
Yeah. If you want to
Pointer.
point,
Okay. Good morning, Professor. Sawadika, professors and distinguished guests. My name is Antaripon. I'm the president of the Thai Institute of Chemical Engineering and Applied Chemistry, and I am also the chairperson of the Chemical Engineering and Petrochemicals of the Engineering Institute of Thailand under His Majesty patronate. I'm working at the Department of Chemical Engineering, King Mongkut Institute of Technology, Lat Krabang. On behalf of enlarge, please. On enlarge, please. On behalf of my department and Thai Institute of Chemical Engineering and Applied Chemistry, Thailand, I would like to invite all of you to join Regional Symposium in Chemical Engineering 2015, which will be arranged in Bangkok on 15-16 October next year, Thursday and Friday. And the next ISCE theme is embracing the opening of ASEAN Economic Community or AEC, incorporating with education, research, and industry in chemical engineering. Topic areas are energy and alternative energy, environmental and safety technologies, and so on. Above all, next year, our faculty will celebrate our 55-year anniversary as well. Please provide your time to join. We accept abstract submission by 15 April and deadline of full paper submission in the end of June. Notification of full paper acceptance on and online registration 15 August. I suppose you have this circulating material and see the details in. Registration fee, of course, include electronic files of extended abstract or full papers, and also conference materials, breakfast, dinner banquet, tea break, something like that. We tentatively book the Swiss Hotel Leather Court, Bangkok. It is 5-star hotel near MRT, close to large shopping centers, and it is very convenient hotel. And this is the accommodation atmosphere of the hotel. And welcome banquet, we will organize at Siam Pyramid. It is a good place to visit. There are pre-show and also a kind of outside pre-show, and also the main 90-minute. It is a must-see shows in Thailand, like journey to the Enchanted Kingdom of Siam. Siam is Thailand. It is a former words of Thailand, and so on. Here are some atmosphere of the show. As the conference will be held in Bangkok, so then you have the opportunity to visit landmarks of Bangkok, such as the Grand Palace, and also many temples, like Temple of the Immoral Buddha, so-called Wat Phra Kaew, and Temple of Dawn. And if you provide or extend your holidays, it is worth to visit our former capital, Ayutthaya, and ancient city. Or if you would like to enjoy Thai culture in the north of Chiang Mai, or in the south of Thailand, please come. Let us welcome you at RSCE 2015. And for the Japanese delegates, Lainenno, an original symposium, listen to Konen Sehi Kite Kudasai. Thank you very much. See you in Bangkok.
Okay, I think that some of you inspired to go already. So for our Somchai 2015, I'll invite Professor Dato' Wan Ramli to give us a briefing. Yeah.
Actually, the 28 now next year, 28 Symposium of Malaysian Chemical Engineers. Actually, it was supposed to be held somewhere else, but yesterday, IChemE Malaysia has decided to let UKM to host the 28th Symposium Malaysian Chemical Engineers. And since it was yesterday, I have no multimedia to show you, although I tried to do last night, but I couldn't make it to work very well, so I'll just do a verbal invitation. So I would like to invite everyone to the next edition of the Symposium of Malaysian Chemical Engineers. It will be held in Kuala Lumpur about the same time as this year's Somche. Probably not the same time as RICE, so that it will allow people who want to attend both to attend both without any problem. We will liaise with the RSC so that we have a different timing, so that we can have that. And the topics are similar to the ones you have here in Taylor's University. Symposium Malaysian Chemical Engineers, the first one was held in UKM long time ago. Yeah, I think nearly 30 years ago, in the 80s, early 80s. So we honored by IChemE's decision to let us host the Symposium Malaysian Chemical Engineers. So I hope everyone will come, especially the Malaysian, but we also would invite our colleagues from ASEAN who want to come to Malaysia. They are welcome, as well as people from Poland, if they want to. Yeah, we will invite them again to the symposium. I think that's all I want to say. So I'll see you next year at the UKM's organized SOMCHI. Thank you very much.
Thank you, Dato'. Just one more thing before we go is to acknowledge our 3 speakers for the keynote sessions today. So I'd like to invite the organizing chairman again, Dr. Chong, to come forward. Okay, so we would like to acknowledge the first speaker, Professor Piasan. Okay, if you could applaud for your appreciation for that talk. Right? And to our second speaker, Professor Dr. Muhammad Ali bin Hashim. And final speaker, Professor Dr. Susan Golado. Okay, thank you everyone. We'll now proceed to our sessions, which are slotted now into 6 sessions, session A9 to A20. So that will take place between 11 to 1. So see you around then. Okay, thank you.
I need to bring. How to disconnect the projector? Because I send this thing unstable. Every time you connect any break. Why you want to disconnect?
Okay. Oh, he's the chair. Ask him later when you lunch break. I am actually